Alright, so today we're going to start with sigma notation. And sigma is just the Greek letter that looks somewhat like that. The Greek letter sigma. So it looks kind of like that, like a straight-edged E. But if I'm writing fast enough, it'll kind of look like that. So, oh, that was pretty good. Sometimes it'll look like that. So you'll see variations of it based on how sloppy I am at the time. Okay, so if we have, let's say, the sum of n terms. Let's say if you have the first term, the second term, the third term, all the way to some nth term, where it's written as the sum from n equals 1, not to infinity, to n, of some a, actually instead of n, let's put I, from I equals 1 to n of a sub I. Okay, so all that means is we're going to start at I equals 1, so that I just becomes 1. Then we're going to go to I equals 2, that should be a plus sign. Then we're going to go for I equals 3, then I equals 4, and we're going to keep doing that all the way to we get to whatever your upper bound limit is. Let me clear up that I equals real quick. That looks a little bit rough. Yep, I equals 1. And this should be a sub 1. Just to make sure it's clear. Okay. Now on this, your I is your index of the summation. Okay. Your a sub I is your, as you could say, your if term of the summation. Okay. And in this case, 1 is your lower bound. And the n, right up here, is your upper bound. All right, so let's say, for example, say if you have the sum from I equals 1 to 6 of I. Okay. That just means you're going to replace I with 1, plus you're going to replace I with 2, plus you're going to replace I with 3, plus you're going to replace I with 4, and then you're going to replace I with 5, and then you're going to go all the way up to 6, and then stop. Okay. Sometimes they'll ask you for the actual one answer after doing all that, but here it's just kind of a process thing. All right, so let's say, for example, if we have the summation from I equals 0 to 5 of I plus 1. Okay, so with this one, we're actually going to start at 0. So you have 0 plus 1. Then you're going to plug in 1. 1 plus 1. Then you're going to plug in 2. Then you're going to plug in 3. Then you're going to plug in 4. Then you're going to plug in 5. And that's where you're going to stop. Okay, so if you look at this one, you have 1 plus 2 plus 3 plus 4 plus 5 plus 6.
So that the index equals 0 on the bottom, that's 5 on the top?
Yes. Okay. So you can see here you have the exact same outcome, but they started off as different summations. All right, so let's say, for example, if you have the summation, let me bring that down a little bit. Let's say from j equals 3 to 7 of 1 over n times, oh, nope, that's the next example. Sorry about that. Say j squared. Okay, sometimes they'll use I, sometimes j, sometimes k. Same thing, just different variable. Okay. So here we're going to start at 3. So that'll be replacing j with 3. So that gives us 3 squared. Then we go up to 4. Then we go up to 5. Then we go up to 6. And then we stop once we go up to 7. Okay. And let's say if we have, for our next example, the sum from k equals 1 to n of 1 over n times k squared plus 1. Okay, so here we're just going to replace the k, because that's our lower bound. Okay, so that's going to equal 1 over n times 1 squared plus 1 plus 1 over n times 2 squared plus 1. Clean that n up a little bit. Plus 1 over n times 3 squared plus 1. And we're going to keep on going all the way till we get to 1 over n. Then we're going to stop at n squared plus 1. Okay. Now if we wanted to, this 1 over n, we could have just factored that right out because we're only changing the k. So that 1 over n just shows up in every term. So we could have just made that 1 over n times 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1 all the way to the n squared plus 1. All right. So any questions on that one?
If that k is just something else, it's just, or...
Oh, you mean for this one?
Oh.
Oh yeah, for this one, like I say, it could be k, it could be j, it could be I. That just lets you know what variable you're going to be changing. So by us having the n there, we're only going to change the k, so that n just stays the same. All right. So any questions on that one? Okay. All right. So clean this up just a bit. Okay, so here we're going to have our summation formulas. Okay, so our first one, we have the sum from I equals 1 to our upper bound of n of a constant, and that's equal to the constant times n. Okay, and for 2, you have the sum I equals 1 to some upper bound of I. That's equal to n times n plus 1 divided by 2. Okay. And we'll actually prove 1 and 2. 3 and 4, the next two, they're proven by mathematical induction, which is a little more complicated. But 1 and 2 proven basically by algebra. Okay, so you have from I equals 1 to n of I squared, that's going to equal n times n plus 1 times 2n plus 1 divided by 6. And for 4, you have the summation from I equals 1 to n of I to the third power. That's going to equal n squared times n plus 1 squared divided by 4. Okay, so we're going to do a quick proof of 1 and 2. Okay, so proof of 1, we have our sum from I equals 1 to n of any constant c. Okay. So let's say instead of just c, let's say if we decided to make that the sum from I equals 1 to n of a constant times x sub I to the 0 power, which is just 1. Oh, let me clear that up just a bit. Okay, so that's going to equal, if you that should be I, not 1. Jumping ahead here. Okay, so if you plug in I equals 1, you just get c times 1. If you plug in I equals 2, you get c times 1. If you plug in I equals 3, you get c times 1. And it keeps on going like that n number of times. Or basically add it n times. Which means if it's added n number of times, it's just equal to n times c. Or c times n. All right. So any questions on that one? Okay. So for the proof of number 2, okay, let's say if we have the sum from I equals 1 to some n of I. If you plug in 1, you're going to get 1. If you plug in 2, you're going to get 2. 3, if you plug in 4, you get 4. 5, all the way to some n minus 2, n minus 1, all the way to some n. So if this would have been 12, we would have started from 1, 2, 3, and all the way to 10, 11, then 12. Okay. So what if we do the exact same thing, I equals 1 to n of I, but we just flip it. So instead of starting at 1, we just go from n to n minus 1, n minus 2, all the way to 3, 2, and 1. All right. So we'll just go ahead and add these two together. So since we're adding these two summations, it's just 2 times the sum from I equals 1 to n of I equals, and we'll add each of these terms together. So if you notice here, you'll have n plus 1. And here, n minus 1 plus 2 is n plus 1. Here, n minus 2 plus 3 is n plus 1. And it's going to repeat like that all the way down because n minus 2 plus 3 is n plus 1. And then that's n plus 1. And that will be n plus 1. So here we have n plus 1 n times. So this gives us, move that up a little bit, sum of 2 from I equals 1 to n of I equals n times n plus 1. Then if we just divide both sides by 2, those two would cancel out. So you end up with the sum from I equals 1 to n of I is equal to n times n plus 1 divided by 2. Okay, so basically we just converted from a function or a summation of I to a summation of n. Okay. So any questions on that one? And you'll see why that comes in handy when we do a couple of examples. Okay. Still writing. All right, looks like everyone's done. Okay, now these are your summation properties. Okay, so they're pretty similar to derivatives where you can kind of distribute it. So let's say with the first one, from I equals 1 to n of x sub I, and it works for either adding or subtracting, so I'll just put that there. And y sub I, you're just going to distribute it to both terms. So it's going to equal the sum from I equals 1 to whatever your upper bound of n is, of x sub I, either adding or subtracting, both works. The sum from I equals 1 to n of y sub I.
Still going on those, like numbers 3 and 4.
Oh no, these are, yep, these are different. Yep. These are just kind of like the properties you can use for each one. They're not actual formulas. The other 4 were the formulas. Okay, so what if you have from I equals 1 to n some constant times some x sub I? Just like with derivatives, you can just bring the constant out to the front. Okay, now we also have, if you have the sum from I equals 1 to n of x sub I, and that is going to be added by x sub n plus 1, you can actually combine these two, because this is going to count all the way up to n, but then you're going to add another n plus 1 to it. So that can actually combine to be from I equals 1 to n plus 1 of x sub I. Okay, and you can separate it also. So let's say you have the sum from I equals 1 to n of some x sub I. You can break it down to the first half, or it doesn't even have to be the half. You can say from I equals 1 to some constant c. of x sub I, and then you can add it, then start off at c plus 1 to n of x sub I. Yeah, it's a little bit crooked looking. Okay, so you can break that down to where you can start off at 1, pick up at any constant. Then as long as you go up to the next constant, or the next, I guess you can call it the integer, and then go up to n, since it will be a whole, an integer. All right, so any questions on that one? All right. Okay, so let's do a couple of examples. Anyone's still writing? Looks like everyone's done. Okay, so let's say, for example, suppose that the sum from I equals 1 to 8 of a sub I is equal to 7. And the sum from I equals 1 to 8 of b sub I is equal to 1. And we want to find the sum from I equals 1 to 8 of a sub I plus 3 b sub I. Okay. So really this is just kind of a test to make sure you understand how the properties all work out. Okay. So we know we can always just distribute that summation. So that gives you the sum from I equals 1 to 8 of a sub I plus the sum from I equals 1 to 8 of 3 b sub I. Okay. And we also know we can get our constant and just bring that right out to the front. So that gives us the sum from I equals 1 to 8 of a sub I plus 3 times the sum from I equals 1 to 8 of b sub I. Okay. So we know our a sub I summation is equal to 7. So we have our 7 plus 3 times our summation of b sub I, which is 1. So we know it's going to equal 10. All right, so any questions on that one? All right.
So on the whole scheme of things for calculus, how
Yeah.
does this rank, like 1 to 10, of knowing and not knowing?
Well, for our
For the
I mean,
test.
Yep.
Okay, but
I
after
mean,
that,
for
I mean, I saw
Count two-
people
count
from Calc
two
2
is
doing,
Yeah.
having sigmas up on their boards when they were doing it
It's
yesterday.
all
and stuff.
completely
And
count two,
plus
like
this
the last time.
this comes up again later today. So this is kind of an introduction, but it really gets deep a little later.
all right, I'm always going to ask those questions too. So.
Oh, not a problem. All right, so let's say, for example, if we suppose that the sum from I equals 1 to 24 of a sub I is equal to negative 10. And the sum from I equals 1 to 5 of a sub I is equal to negative 4. And we want to find the sum from I equals 6 to 24 of a sub I. All right, so the one thing we know right from the beginning, before we even start with the values, is the fact that our sum from 1 to 24 of a sub I can be broken down. Okay. So we see here that this one stops at 5, and this one starts at 6. So we can just break that down to the sum from I equals 1 to 5 of a sub I plus the sum from I equals 6 to 24 of a sub I. So we still counted from 1 to 24. We just took a little skip. So we have from 1 to 5, then from 6 to 24. Okay. But we're solving from 6 to 24, so we want to isolate this one. So we subtract from 1 to 5 on both sides. So from I equals 1 to 5, from I equals 1 to 5, a sub I, where these two cancel out. Okay, so that gives us, make sure I have enough room, the sum, just going to switch them around, from I equals 6 to 24 of a sub I is equal to the sum from I to 24 a sub I minus the sum from 1 to 5. Okay. And as we had to do that because remember all of our properties only worked when you had a lower bound of 1. Okay, so that means we can get this. We have our negative 10. I'll write it underneath it. So we have negative 10 minus, from 1 to 5, that was negative 4. Okay, so you end up with negative 6. We just had to kind of manipulate the properties a little bit. All right. So any questions on that one? All right. Okay, so let's say for our next example, let's say if we had to evaluate the sum from I equals 1 to 15 of 5i minus 4. Okay, they're not going to give us any values or anything like that. We have to find out all on our own. Okay, so with this one, you're actually going to use two formulas. Okay, so you have the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. And we also know that the sum from I equals 1 to n of a constant is equal to n times that constant. Okay, so with this, we're just going to go ahead and distribute our summation. So you have the sum from I equals 1 to 15. And we can bring our constant out, so we can just make that 5 times I. We'll bring that, clean that up a little bit.